Hey everyone, in this video we're still on chapter 4. This is the last video for chapter 4 and I have to say this is the most important topic in chapter 4, right, which is conservation of mass. You're going to use this theory if you pursue your studies in fluid mechanics. You're definitely going to be using this theory a lot. Okay, so the principle of conservation of mass states that matter cannot be created or destroyed. Just like energy, mass also cannot be created or destroyed. Okay, and of course matter is measured in its mass. How much matter? How many kilograms? So this principle is used in analysis of flowing fluids or flows. And if you apply this principle to a certain region, for example, a pipe that is transporting water can be very, very long, many kilometers. So it's impossible to study the entire length. So we just take a portion of it, maybe just 1 kilometer of it, or even 2 meters of it. Okay, we call it our fixed region, and this is a control volume. So we only study this control volume. So for that particular region in the pipe, the mass entering the region minus the mass leaving the region will be the difference in mass that is left inside the region. Okay, this sounds very simple. So whatever enters the system minus whatever leaves the system will be what stays inside, right? So another example, you have this bathtub. Let's say you put 50 kilograms of water in. At the same time, you drain out 30 kilograms. Obviously, what will be left inside is 20 kilograms. So that is the principle of conservation of mass. Okay, for a steady flow, remember steady flow is when things are constant over time. There is no increase in mass within the control volume. Okay, because everything is constant over time. So mass entering minus mass leaving equals to the difference in mass. We saw this in the previous slide. So let's say that the difference in mass here equals to 0. Alright, then what we have is mass entering will be equal to mass leaving. Okay, from the first equation, this is 0, therefore you move the mass leaving to the other side, you get this equation. Whatever enters is equal to whatever leaves, because nothing nothing changes inside. So this can be applied to a stream tube such as the one shown here. Okay, whatever enters here, in the entrance, it has a certain density, moving at a certain velocity, and the area is such. Okay, and at the exit also it has some density, a certain velocity, and some area. So whatever that enters here, even though this value of density, velocity, and area might be different for both ends, but whatever enters will also leave in the same amount. Okay, so for compressible fluid, we have something called the continuity equation. So for compressible fluid, remember compressible is when you can compress it, that means its density can change. So for compressible fluid, the mass flow rate at the inlet equals to the mass flow rate at the outlet, which means that the mass flow rate is constant. Okay, mass flow rate here equals to mass flow rate at the outlet. That is for compressible fluid. And the mass flow rate equation is rho AV. Please remember this, very important equation. Okay, rho AV, rho is of course the density, A is the area, and V is the velocity of the flow. So this, each of these terms might have their own value at the inlet and outlet respectively. Okay, so you can expand m dot to rho AV, and we have this equation. Alright, this is the continuity equation for compressible fluid. Now, what if we have incompressible fluid where the density is constant? For example, this is an ideal fluid, let's say water. In that application, its density remains constant. So we can simplify this equation. So from rho AV1 equals to rho AV2, what we can do is we can cancel out rho because it's constant. It will not affect this equation. So you're left with A1 V1 equals to A2 V2 in this equation at the bottom here. And remember that AV is Q. Q equals to AV. You've seen this in the previous video. So in incompressible fluid, the volume flow rate is equal. But if the density is not constant, you have to use this equation, the mass continuity. Okay, a very short example. A garden hose attached with a nozzle is used to fill a 10-gallon bucket. The inner diameter of the hose is 2 cm and it reduces to 8 cm at the nozzle exit. So basically we have something like a nozzle. Okay, the inlet is 2 cm diameter and the outlet is 0.8 cm diameter. If it takes 50 seconds to fill the bucket with water, you have to find the volume and the mass flow rate of the water through the hose and the average velocity of water at the nozzle exit. So we have to find three things. Okay, so here is what is the volume flow rate, what is the mass flow rate, and here what is the velocity at the outlet. Outlet means here, velocity at the nozzle outlet. Okay, so for the first part, to find the volume flow rate and the mass flow rate, volume flow rate, okay, that could be confusing. So let's change this to Q. Okay, volume flow rate equals to volume over time. So even though we want to calculate the volume flow rate from the pipe, but we know that whatever leaves the pipe goes into the bucket. So the volume that we are actually measuring can be referred to as the volume of the bucket. So 10 gallons, you can convert this to liters or meter cube if you wish. Divide by the total time taken to fill up 10 gallons. So we get the volume flow rate. The mass flow rate, you don't have to separately calculate this because you know that density equals to mass flow rate over volume flow rate. Again, this V dot is same as Q. Okay, density of water, you know this very well. You can also write it as 1000 kilograms per meter cube, and this is the volume flow rate. You get this answer. Alright, the average velocity of water at the nozzle exit. Okay, where do we have the equation for velocity? Of course, in mass flow rate equals to rho AV, or volume flow rate equals to AV. Okay, so we need to find the area first, and the area at the nozzle exit has to be based on, of course, the diameter of the nozzle or the radius of the nozzle at the exit. Remember, there were two diameters given. So we take the exit diameter, you calculate the area. And then the average velocity, here we are using the Q equals AV. Alright, we're using Q equals AV. You can also use mass flow rate equals to rho AV. You'll get the same result. So rearrange velocity equals to volume flow rate divided by area. Again, this can be replaced by Q, Q over A. Substitute the values. See, this one is conversion from liters to meter cube. You can do it from the beginning if you want. And then we get the final answer. Okay, so that's pretty much it for chapter 4. I will put up some practice questions. Actually, you can find them in the PowerPoint slides in week 5 folder. Okay, and then maybe when we meet, you can ask questions based on the practice questions there. Okay, see you guys.